All right, Mrs. Blenda here with our last lesson on exponent properties. This is another quotient property, but it's pretty simple. It's very similar to our powers of powers. This is powers of quotients. Now, powers of quotients works in the same way as our powers of powers. If I have more than one base, in this case, our base are top and bottom of a fraction line, then each base gets the exponent on the outside. And my little example illustrates this. That means if I have 2/3 to the 5th power, I actually have 2/3 multiplying 5 times. So there's 5 2's and there's 5 3's all multiplying. So it acts exactly the same way as our powers of powers that we had before. More than one base on the inside of those parentheses, everyone joins in the fun. More than one, everyone joins in the fun. Working just the same way that our powers of powers did. So our first example, 2 to the 3rd, 3 squared. Everything to the power of 2. That means that this power will come in to each base on the bottom. Of course, each base on the bottom is already a power. So if I have that exponent on the outside, then I have to multiply it with the exponents on the inside. So I will multiply it for the top. So 3 times 2 gives me 6. So now I've got 2 to the 6th power, and I multiply it on the bottom with the exponent there. 2 times 2, oops, base of 3 stays the same. 2 times 2 gives me 4. So there is my final answer, 2 to the 6th power over 3 to the 4th power. Okay. Anytime I've got more than one base on the inside of the parentheses, everybody joins in the fun. And if the parentheses are surrounding a fraction, then everyone joins in the fun, top and bottom. So our second example illustrates this very nicely. This exponent will come to this base of A. It will multiply with the exponent already on the base of B. So 4 times 5 gives me 20. And will also multiply to the bottom. So 2 times 5 gives me 10. And then our base of D already has an exponent of 3. 3 times 5 gives me 15. So everybody gets a piece of that exponent on the outside. Everybody joins in the fun. Okay. Last example here. Same thing. If the exponent is on the outside and the parentheses are touching the entire fraction, then that exponent has to go to every base on the inside of the fraction. So there are 2 ways that I can take a look at this. I can work from the outside in or the inside out. I'm going to start with the outside in because that's what we were just doing. So that means that I have 3 times 3 gives me a to the 9 and b to the 3rd. On the bottom, I will have 3 times 2 gives me 6 and 3 times 2 gives me 6. Now I still have the same base, top and bottom, so I have to use my quotient rule that we learned before, which means I'm looking at a to the 9 minus 6 and b to the 3 minus 6. So 9 minus 6 gives me 3, and 3 minus 6 gives me negative 3. A negative exponent means that base is on the wrong side of the fraction line, so that one will have to drop below. And there is my final answer. Well, what if I wanted to work from the inside out instead? What if I wanted to use my quotient rule first and subtract those exponents? We absolutely can. Let's take a look at what that would look like. So if I work from the inside out, and I'm looking at that quotient rule we learned before first, looking at these similar bases, I would have a to the 3 minus 2, and I would have b to the 1 minus 2. That means in parentheses to the 3rd power. So looking on the inside, I will have a to the 1 and b to the negative 1. So let's distribute that 3 to the inside to each of them. So now I've got a to the 3rd and b to the negative 3. And look at that. I ended up in exactly the same spot we did before. So as I have said before, it doesn't matter which order you use your quotient rules or any of your exponent rules. If you're using an exponent rule correctly, it's all going to come out to the same simplified answer in the end. It doesn't matter which order you use them in, because all the exponent rules can be used in any order. Okay? All right, let's take a look at these additional examples. Oh, let's get this, it's a little bit cluttered. Let's get that out of there. Okay. So this one, this first example has a negative exponent. So let's see what happens when I have a negative exponent. Let's just distribute it in just like it was the same as a positive one. So I've got 3 to the negative 2 now, and 4 to the negative 2. Of course, a negative exponent means that they are on the wrong side of the fraction line, so that 4 squared needs to come up, and the 3 squared needs to move down. So our final answer is 4 squared over 3 squared. Okay. So it's kind of like taking our negative exponent rules and our quotient rule and putting them together into one. Okay. Process is still exactly the same. Just keep chugging through it. All right. So now I've got this exponent of 3. I'm going to go ahead and bring that in. So I will have x to the 6 and x to the 3 and y to the 9. Because I have x to the 6 and x to the 3, I need to make sure that I combine those. I can't have more than one base in the same expression. So I'm really looking at x to the 6 minus 3. So 6 minus 3 is just 3. And the y to the 9 stays the same because it didn't combine with any other bases. So there's my final simplified answer, x to the 3rd over y to the 9. Let's take a look at this next one. I've got that exponent on the outside, so I need to remember to multiply it with the exponents on the inside. That gives me x to the 6. 3 times 2 is 6. Negative 3 times 2 gives me negative 6. And there's that y to the 3rd still on the outside. And I still have x to the 4th. All right. Now I see that I have a couple of the same bases here. I've got an x here and an x here, so I can go ahead and add those exponents. So for my next step, I'm going to add those. So 6 plus 3 gives me 9. I still have y to the negative 6. I'm going to have to take care of that negative in a minute. And x to the 4th. I have more than one base of an x, so I need to make sure that I'm using my quotient rule to subtract those. So 9 minus 4 leaves me with x to the 5th. And of course, that x to the negative 6 is on the wrong side of the fraction line, so that one needs to move down. So there is my final answer. Okay. All right, 2 more examples. Oh, I've got a couple of parentheses over here. So I'm going to deal with the inner parentheses first, where I have this negative 2 touching the inner parentheses. So I'm going to multiply that with the exponents already on the inside, one outside, so I have to multiply. So I'm not going to touch that one on the top. That one's going to stay the same, and I'm not touching this exponent on the outside. I'm just taking care of the bottom. So negative 2 times 3 gives me negative 6, and negative 2 times 1 gives me negative 2. Then I'm going to distribute the negative 2 on the outside to the inside. So now I have a to the negative 6. Negative 6 times negative 2 is positive 12. And negative 2 times negative 2 is positive 4. Because I have this negative 6 exponent on the a on the top, that means that it actually needs to go down to the bottom. So I have a to the 12, a to the 6, and b to the 4. Well, because these exponents are in a line, I can add them to combine. So I actually have 1 over a to the 18 and b to the 4. Again, you can use those exponent rules in a different order and still get to exactly the same answer in the end. There's nothing wrong with that. All right, just want to clean up the space a little bit here for this last example. Again, I have some parentheses on the bottom that I want to go ahead and take care of first. So because I have that exponent on the outside, I'm going to multiply it with the exponents on the inside. I'm not going to change the top at all. I'm just going to rewrite it exactly the way it already is. Those fours are a little light there. There we go. So then I'm going to make sure that I multiply that -4 with the 2 for -8 and with the 3 for -12. And nothing happened with the 2a squared. That's going to stay the same. All I did was take care of those parentheses. Now I want to take a look and combine my bases that are in a line. So I'm still looking at this bottom where I have an a base here and an a base here. I'm going to go ahead and add those exponents to combine those bases into one spot. So again, I'm not doing anything with the top. I'm just rewriting it so I don't forget about it. And -8 plus 2 leaves me with a to the -6. And I've got b to the -12. Okay. We've got a couple of options here. We can go ahead and use our quotient rule and subtract those exponents. Or we can pay attention to our negative exponent rule and move our negative exponents. I personally like to move the negative exponents because I hate dealing with double negatives in the quotient rule. So for this next step, I'm going to flip all those powers with negatives to their proper sides. So that 2a to the 4th stays. The b to the -4 has to go down. The a to the 6 moves to the other side, and the b to the 12 moves to the other side. There we go. Now I've got all positive exponents to deal with. That's much easier for me to look at. So now, again, I've got those like bases on the top where I can add those exponents to combine them. 4 plus 6 gives me 10. And these b's, top and bottom, I'm going to have to subtract those. So I've got that b to the 12 minus 4. That is going to leave me with 2a to the 10th power and b to the 8 as my final answer. There we go. And that's using all of those exponent properties to get to a simplified answer with only positive exponents, each base showing only one time, and our numbers as simple as possible with no parentheses. And that is our quotient rules.